our presentation is on slope fields, and it is by Johnny Ocampo, Kayla Navarrete, Lucero Quintana, and Hina Patel. So, slope fields are graphs that can obtain solutions to a first-order differential equation without solving the actual differential equation. Since a differential equation gives the slope at any point x, y, we can use that information to draw a small piece of linearization at that point, which can approximate the solution curve that passes through the point. The graph I have here is an example of a slope field, and the little dashes are the different slopes at their corresponding points. The dashes here evidently give you the general solution to the differential equation.
Constructing a slope field. Use your differential equation to calculate x values, y values, and their slopes at those corresponding points. To do this, make a table of sample x values, y values, and slopes. The x values you can choose randomly, and it doesn't really matter what values you use. However, that being said, be smart about it and keep your values rather close to the origin and easy to work with. On a test or on the AP exam, you will be told what values to use. The slopes are found by putting those x values into the differential equation. Draw this on an xy plane. At each x value, draw a short tangent line whose slope corresponds to the slope in your chart. And an example of this would be from a quiz that we took in class. So it says to consider the differential equation dy dx equals 2x minus y. On the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So the first thing I did was make a table of the indicated points, putting their corresponding x and y values in this said table. Then I plugged those values into the equation to find the slope at that given point. From there, I drew the slopes at their respective points on the graph.
Matching slope fields with differential equations. Here I have an example from the book, and it says in exercise 35 through 40, match the differential equation with the appropriate slope field. For 35, we have dy dx equals x. The slopes will only depend on the x value, therefore all points with the same x value must have the same slope, which is why C is the one that matches the differential. 36 is dy dx equals y. The slopes will only depend on the y value, therefore all points with the same y value must have the same slope, which is why E is the one that matches the differential. 37 is dy dx equals x minus y, where x minus y equals 0, thus making x equal y. And because x equals y, we can discard B and E because they have slopes of 0 at all points on the x-axis, and then we can discard C and F because they have slopes of 0 on all points on the y-axis. We're left with A and D as our choices, and then we can use our point 32 and plug it into our differential to get 1. Because it's positive, the slopes around it must be positive too, and A is the only option that has positive slopes around that point. For 38, it has dy dx equals y minus x, where y minus x equals 0, making x equal y. We can eliminate B and E because they have the slopes of 0 at all points on the x-axis. C and F can be eliminated since they have the slopes of 0 on all points on the y-axis. And we're left once more with A and D as our choices. We take our point 32, plug it in, and we'll get negative 1. Option D is the only one with a negative slopes around our point, which makes match our differential. For 39, we have dy dx equals negative y over x. When y equals 0 and x does not equal to 0, the slope is negative y over x equal negative 0 over x equals 0. Graphs A, C, D, and F can be eliminated because they don't have the slopes of 0 when y equals 0. Now, if you consider the point 32 and plug it into our differential, you'd get negative 2/3, meaning the slopes around have to be negative, and because in E, the slopes around are positive, B is the one that matches our differential. Lastly, for 40, we have dy dx equals negative x over y when x equals 0 and y does not equal 0. The slope is negative x over y equals 0 over y equals 0. Graphs A, B, D, and E can be eliminated because they don't have slopes of 0 when x equals 0. Now, if you consider the point 32 and plug it into our differential, you'd get negative 32, meaning the slopes around have to be negative, and because in C the slopes around are positive, F is the one that matches our differential.
So now let's take a look at a second example. We have this question here taken from the homework. We have, shown above is a slope field for which of the following differential equations. So a way to tackle these problems is try to look for common patterns you can identify in the graph. If we look here, on the y-axis, all the slopes are 0. So every time x equals 0, dy dx equals 0. So let's try to look at the equations and see which ones we can eliminate. If we look at A, and we plug in 0 for x, you have 0 times y is 0, and then minus x, which is 0, you end up with dy dx equals 0, so that passes. With b, you have, again, 0 times y, which is 0, plus x, which is still 0, and you end up with dy dx equals 0. That one also passes. For c, we have dy dx equals y minus x squared. And if we do 0 squared, you end up with dy dx equals y. So this equation is saying that the x value doesn't matter at all, so that's wrong. If we look at d, you have dy dx equals x squared times the quantity y minus 1. So if x is 0, that makes dy dx equal to 0. So d is still good. And if we look at e, you have y minus 1 the quantity cubed, which doesn't account for x, so you can eliminate that as well. So right now, we have eliminated c and e. We need to find between a, b, and d. So let's take a look and try to find another trend in this graph. As you can see, as x becomes more negative on this y-axis here, the dy dx becomes more positive. So you see here, x becomes more negative, the lines become more vertical. So as x gets more negative, dy dx gets more positive. Let's see what graphs that matches with. We have y is going to be equal 0 along this axis. So we have x times 0, which is 0, minus, and if we have a negative number, it's getting more and more negative. A negative times a negative is a positive, so this is going to be getting more positive. So dy dx increases as x gets more negative, which is good. That matches the criteria. Let's look at b. We have x times 0, which is 0, plus, if x is increasingly negative, plus a negative number just means dy dx is decreasing. So that would be a decreasing slope, which is wrong. That eliminates b. If we look at d, and y is 0, then we end up with negative 1 times x squared, which is just negative x squared. And if we have a negative number, and x is getting more and more negative, this is going to be getting more and more positive, but we have that negative in front. So that means dy dx gets more negative. So we can eliminate d as well, leaving a as the only answer. And if we look here, we can actually solve the differential equation to show how you can get a general solution for the problem. So we ended up finding out that the differential equation for this problem, we had dy dx equals xy minus x. So here is all the work for it. I could explain it, but we already saw a presentation on differential equations. So you can see we end up with y equals e to the x squared over 2 plus c plus 1. And I sketched the graph out here. So if you look at this sketch of this graph, and you look back at our slope field, you see the resemblance here. So this sketch of the graph is a potential solution to this slope field when the constant is 0. Let's look at a third example. So this problem says, shown above is a slope field for which of the following differential equations. If you notice on all of these lines, the x isn't influencing the slope at all. So if you look at y equals 2, all the slopes are the same here. Y equals 4, all the slopes are the same here. So the slope only changes when y changes. That gives us an immediate clue when looking for our answer choices that we don't want to see x in our equation. Immediately that eliminates a and c, as both of them feature x in the differential equation. So now we need to test a couple points with differential equations b and d to see which one matches better. So let's look at y equals 2. So if we plug in 2 to b, we get 4 minus 2, which is 2, times 2, which is 4. 4 over 4 is 1. So at y equals 2 for b, we should see a slope of 1 if this one was true. Let's look at d. We have dy dx equals y squared times 4 minus y over 4. If we plug in 2 here, we have 4 minus 2, which is 2. 2 squared here is 4. 4 times 2 is 8. 8 over 4 is 2. So this is saying that we have a slope of 2. So if you look here, what slope does this mostly resemble? To help, I put what a slope of 1 would look like, which is right here, and I put what a slope of 2 would look like, which is right here. As you can see, the slope of 2 matches better, so the answer would be D. And any questions? Feel free to let us know.